The first lesson on a recovery ship is this: the deep ocean steals time. It steals heat first, then voices, then the bright color of life until only shapes remain. Silencers made of pressure and salt. Survivors know it, scientists know it. Salvage teams measure it down to the 10th of a degree and plan around it. So when we dropped a thermistor onto a wreck and the readout blinked above ambient, nobody laughed. I was on the recovery team, crew of a deep submersible support vessel that a Navy office quietly called into service when something important hit the bottom. We had a crew of technicians, a pilot for the manned submersible, ROV pilots, and a small, efficient supply of engineers who knew how to make winches and hydraulics behave when the ocean tried to shred them. Our platform carried a pressurized working sub, a tethered, remotely operated vehicle, and a pile of gear the manuals called emergency ship salvage material. Our job, on paper, was simple and sterile. Locate, document, lift if required, and hand over to technical authorities. In practice, it was a marathon of patience, planning, and improvisation under pressure. The manuals taught you the tools. Experience taught you to trust the instruments that didn't have human faces. So let me give you the environment first. The deep ocean we worked in, the abyssal plain where this call took us, sits in a kind of elemental cold. Below the sunlit surface, water temperatures fall quickly and then flatten. In most places, below a few hundred meters, the temperature stabilizes near freezing, typically 0 to 3 degrees Celsius at abyssal depths. That matters because water is a prodigious heat sink. Its high specific heat capacity and density mean heat transfers away from objects fast, especially if the object is exposed and surrounded by moving water. Under normal circumstances, wreckage equilibrates to ambient temperature quickly. Hot metal cools, and life goes cold within hours to days, depending on mass and insulation. So a warm reading at 4,000 to 5,000 meters is something you file under unlikely and then urgent. We reached the site, lowered our probe, and the readout came back 0.8 degrees above the surrounding water, above ambient at 14,000 feet. That short sentence, a fractional degree, is why salvage teams run like a hive when called. There are reasons to find something warm on the bottom: internal decay, geothermal activity, ongoing chemical reactions, or in the worst case, surviving heat from engines, batteries, or even people. For every hypothesis, there is a set of instruments, procedures, and safety boxes to tick. The U.S. Navy's salvage manuals lay it out. Deep ocean recovery is a matrix of search, classification, and controlled retrieval. Anomalies change risk profiles and require immediate escalation to technical authority. We began to treat the wreck as an active target the second the probe warmed. Let me take you through the mission the way we lived it: the call-in, the transit, the search, the identification, and the slow, careful approach that turned into the kind of day you know you'll remember for the rest of your life. We were awakened at 0200 by the duty officer. Coordinates, last known telemetry, time of loss. A classified platform had lost contact during a test. We weren't told everything. That's common. The chain of custody and the need to know carve up the story so that those who must make decisions get only what they need. We prepared by checklist: rig the chassis for the submersible, test the tether winch, calibrate the ROV's temperature and chemical sensors, and route the ship's satellite comms through an encrypted channel to the sponsor. Soup Salve doctrine is explicit about preparation. You must be able to shift from surface search to deep recovery architecture in hours, and your equipment must be ready even before the drop. Transit to the search box is boring in the best way. Fix to fix on charts, course corrections only when satellite fixes disagree, and the coffee turning from hot to mechanical. We plotted an initial search pattern keyed to last known positions and dead reckoning drift. at depth profiles of temperature and sound velocity were requested in advance. The ocean's vertical layers bend sound and change the ROV's telemetry characteristics. We dropped expendable probes to log thermocline layers for our mission planning. The sound speed profile informs how we run the acoustic tracking and how we interpret echoes. Those apparently academic curves are, in a salvage dive, the difference between seeing a target and watching it hide in the acoustic shadows. When we arrived over the nominal bearing, the sea surface hid everything like a blank sheet. The work happens down where the light fails. ROV pilots see only what the cameras and sonars return, and the white line on the map is an argument between probability and resource allocation. We deployed the ROV first, a low-risk, long-endurance vehicle with a grappling arm, lights capable of spotlighting a baseball field in the dark, and an array of sensors, high-definition cameras, a forward-looking sonar, useful when visibility is nil, a micro-CTD probe, methane and hydrocarbon sniffers, and most importantly for this case, a high-accuracy thermistor that would log temperatures within 0.01 degrees Celsius. The thermistor is slow and faithful. It tells the truth without the need for translation. The initial ROV sweep was procedural. The sonar returned shapes, a shadow at bearing 138 degrees, a smear that could be wreckage, a metal ridge, then nothing. Pellets of silt rose when the skiff of our thrusters passed. The bottom was a flat field of ooze. Then we saw it on the forward sonar, an angular silhouette the size of a small vessel. The camera zoomed in, and in low-resolution green-black, we saw plating and a hatch rim. The ROV hovered, and the pilots executed a standard approach. Lights low, forward lights angled so reflections don't blind the camera, manipulator idle. Then the thermistor went into the water around the structure and read higher than the nearby seawater. We repeated the measurement on a second probe, still warm. That duplication is important in fieldwork. It turns a fluke into a verified anomaly. Why does a warm wreck matter so much? Because temperature is a primary tracer of energy flow. There are only a handful of things likely to inject heat into a deep-sea object. Residual decay heat from onboard systems, like batteries or reactor components, exothermic chemical reactions, corrosion processes can be mildly exothermic, but rarely enough to measure like this. Hydrothermal activity, vents, microbial metabolism in unusual blooms, or later stage events like fires that continued after sinking, rare at abyssal depths. Each possibility maps to a different operational risk and political implication. Reactor heat implies radiological considerations. A live battery fire implies toxic gases and potential explosion risk if the vehicle is disturbed. Hydrothermal sources imply natural geology. An active engine or heated residuals could mean survivors or a delayed emergency. So the warm reading forces you to ask the hardest question first: is this site safe to approach? We followed the checklist. Step 1, halt any physical interaction. Step 2, run a 360-degree sweep with the ROV's methane and hydrocarbon sensors while keeping the camera at a respectful station-keeping distance, about 2 to 3 meters for a high-res look. Step 3, complement thermal readouts with chemical sampling. Our ROV carries a syringe for in-situ water sampling and a small mass spectrometer to detect volatile species. The thermistor stayed elevated. The water sample showed slightly elevated dissolved organic signatures consistent with recent contamination from hydraulic fluids, and the hydrocarbon trace was low but measurable. Nothing screamed reactor, but the chemistry said recent anthropogenic activity. That made the command post lean forward.
forward. Concurrently, we ran acoustic classification. Every metallic object has a signature when pinged. That signature depends on hull shape, thickness, and internal cavities. It's how the SOUS networks once identified different submarine classes by their harmonic content. We switched to a passive listening mode and recorded a low-frequency band for a long dwell listen. Nothing moved. There was no motor whine, no cavitation, but there was a faint, irregular thud. Our acoustic analysts thought it might be settling strata or the collapse of internal voids. That, by itself, is not a go, no-go, but put together with thermal and chemical anomalies, it becomes a dossier. At this point, the operation shifts from a routine dive to a formal salvage incident. SUPSalve doctrine requires a technical authority, TA, be notified. If the object is military or sensitive, the chain of command is instantaneously higher. We fired our encrypted feed up the chain and prepared to follow orders. The TA demanded a higher fidelity of evidence, longer thermal logs, discrete water samples at multiple distances from the wreck, and a full photo mosaic. We obliged. ROV pilots spent hours stitching images, pulling 3 independent syringe samples, and dropping a tethered temperature probe into any opening we could find. The results narrowed the possibilities. Thermal gradient. The object's exterior logged 0.6 to 1.0 degrees Celsius above ambient for a radial distance of roughly 30 to 50 centimeters from the hull surface. Beyond that distance, the water reverted to ambient. The chemical signature included trace hydraulic oil and elevated dissolved carbon signature consistent with recent organic leaching and warm metal oxidation. There was no elevated gamma count in our preliminary scan. Radiation monitors read background levels. That was a relief, but the anomaly remained. Something about this object had retained heat long enough to be measured at depth by our instruments.
So what physics explain a warm object on the bottom? Let's be methodical. Metal cools by conduction to the surrounding water and by convection when water is moving. The rate depends on the object's mass, specific heat capacity, surface area to volume ratio, and the rate at which seawater sweeps across the surface. In still water, a massive steel object will cool more slowly than a slender part, but in the deep ocean, the tiny currents and microeddies, plus our own ROV's thrusters, accelerate cooling. Therefore, to sustain a measurable warm boundary layer requires an internal or continuing external heat source. Absent active heating, the only plausible anthropogenic candidates are recent electrical battery heat, continuing chemical reaction, or biological processes, unlikely to produce a full degree increase in deep water. A hydrothermal vent can easily create that signature, but our geology survey showed no venting structures nearby. We were left with the inference that the wreck had either carried residual heat into the descent, thermal inertia, or some onboard system had continued dissipating heat after impact. Thermal inertia is a credible, non-sinister explanation for short intervals. A large mass at 400 degrees Celsius will take time to equilibrate, and a heavy insulated object, say an engine block wrapped in thermal barriers, can remain warm for hours or days. Ships and aircraft contain enclosed spaces and insulating materials, paint, fuel residues, thermal blankets that delay heat escape. Deep recovery teams treat inertia as a baseline hypothesis. You estimate the time since loss and model how long cooling would take. If the calculated relaxation time matches the measured anomaly, the case closes to expected. But if the measured warmth outlasts the model or appears inconsistent with expected energy content, you escalate. In our case, modeling the wreck as a typical mid-size aluminum/hull object with no ongoing heat source predicted cooling to ambient well before our arrival at the timestamp we were given. That mismatch kept the incident hot in the logs. Another practical route to warm wreckage is battery heat.
Modern vehicles, unmanned systems, test rigs, even small craft often carry lithium-based batteries that can generate significant heat during a thermal runaway. Cells can self-heat, vent, and burn even in deep water if their insulative casings delay quenching. If an object suffered a battery failure as it sank, the battery ensemble can still radiate heat into the hull for hours. This is why ROV pilots carry hydrocarbon sniffers, and salvage manuals insist on cautious approach and remote manipulations before breaching hulls. We treated the possibility of battery heating seriously. It implies chemical risk, venting gases, and an elevated chance of secondary events if you disturb the structure. The thermal and hydrocarbon results were consistent with that scenario, but not conclusive. We also considered corrosion and exothermic oxidation. When certain metals oxidize rapidly in seawater, particularly when they encounter trapped pockets of reactive substances, the chemical energy release is measurable as heat. In wrecks containing fresh reactive materials, the interactions between seawater, metals, and trapped organics can create hotspots, but the mass and energy scales required to keep a 1-degree delta over a radius of tens of centimeters are significant. We'd need either a large reactive mass or ongoing oxidation under constrained conditions. The water sample's chemistry suggested increased dissolved organics, but not the extraordinary chemistry you'd expect from massive exothermic corrosion. That weighed against this possibility. We also briefed the human risk policers. What if people or systems were alive? In recent history, there have been rare cases of survivorship in enclosed submerged spaces. Survival depends on pockets of air, access to stored oxygen, and the avoidance of toxic combustion products. Deep salvage teams plan for very low odds of live humans at extreme depth, but even the remote possibility forces a different posture entirely. It changes legal obligations and the urgency of lift. In our case, the lack of sonar movement, the absence of audible human sounds on sensitive hydrophones, and the chemical profile argued against survivors. Still, SOP required that we collect definitive interior video before any physical breaching, so we pivoted to a delicate approach. The ROV's manipulator can open small inspection hatches, nudge panels, and feed fiber optic borescopes into narrow apertures. We risked a single-thread inspection, a borescope down a seam to peer into an internal cavity. The manipulator eased the camera into a splice, and the engineers held their breath as pixels resolved. We saw insulation blankets, a pylon structure, and, startlingly, what looked like recent scorch marks along an interior bracket, and a residue that our in-situ spectrometer tagged as burnt electrolyte. The interpretation tightened. Electrical arcing or battery thermal event had likely occurred inside, and the wreck's insulation delayed heat loss long enough for us to measure it at depth. The evidence shifted the problem from geology to forensic engineering. That forensic conclusion was still not comfortable from a safety perspective. A battery thermal event implies possible combustion byproducts, pressurized oxygen pockets in enclosed volumes, and an elevated chance of secondary events if you disturb the structure. SUPSALV's manual prescribes strict mitigations: remote lifting with a containment bell, slow, controlled cutting of hull with hot wire or water jet, and on-surface quarantine for recovered objects. We had to design a plan that protected the ship, the crew, and the environment. It took hours of conference calls, annotated mosaics, and a consult with the payload's engineering authority. They asked for evidence of packaging and manufacturer data that would confirm the chemistry. We prioritized a controlled lifting plan, attach a lift collar around the midsection rather than a direct external cut, minimize hull breaches, and surface the object for full forensic teardown in a controlled pier environment.
The lift itself is a ballet of winches, strain calculations, and slow tension management. At depth, the lifting lines must avoid shock loads that would spit the object free or cause catastrophic failure. We rigged a dual collar system with distributed slings and a soft capture net that would cradle rather than puncture. The ROV threaded the slings under the structure, and we took 5 hours to cinch them in place, continuously monitoring the thermal log. As the lift began, the thermistor continued to read a delta, but the peak only slowly decreased. During ascent, the water's pressure decrease changes convective patterns, something the models warned us about. But the onboard data showed the warmth fading in a curve, consistent with a large internal energy store, slowly losing heat. The ship's deck crew braced as the recovered object broke the surface, and we craned it into a quarantined cradle. On deck, the real work began. The object's identity was verified. It was a test vehicle with a high-energy battery pack and several telemetry nodes. The forensic team opened the internal bay in a specially designed hood and under controlled ventilation documented charred cell arrays and vented electrolyte. The radiological monitors remained quiescent. The battery pack had experienced a thermal runaway event that had continued as the vehicle sank. The insulated compartments and the water's pressure delayed oxidation and heat transfer, so the mass stayed measurably warm long after hitting the bottom. In short, it wasn't supernatural. It was chemistry, insulation, and depth conspiring to make a faint but actionable heat signature. When explained like that, the case is less eerie, but no less consequential. The lessons were operational and procedural, not metaphysical. We filed the report with detail: thermal stamped logs, chemical spectra, acoustic files, a photo mosaic, and a step-by-step lift plan. Subsalve's archive would keep it as a learning case: how battery chemistries and insulation change risk models for deep recovery, how to plan for thermal runaways underwater, and how to update containment protocols to include venting risk on deck. The after-action also flagged procurement changes. Industry needed to mark battery enclosures with greater telemetry and with intentional vent paths for emergency conditions, because the deep ocean is terrible at forgiving hidden heat. There are quieter takeaways that mattered to the crew. One petty officer who had been a quiet presence on the tether winch told me later that he'd replayed the thermal log on his off watch and realized how small numbers had saved our lives. A 2-degree delta, a 0.01 degree Celsius change, an anomalous hydrocarbon trace, tiny things that moved procedures from routine to containment. He said he'd never thought about how patient the sea must be to cool a hot wreck, how for a time the ocean can be complicit in preserving an energetic event. For us, the moral was simple: respect the instruments, escalate early, and design recovery plans that assume the worst until proven otherwise. If you want the technical anchors for what we did and why it worked, here are the core points we used in every debrief. Deep sea ambient temperature. Below the thermocline, it's typically near 0 to 3 degrees Celsius. This high heat sink effect means lingering warmth is atypical and significant. Salvage doctrine, subsalve manuals, and naval salvage practice require escalation when anomalies show active signatures. Treat thermal anomalies as potential energetic events until forensic analysis proves otherwise. Heat transfer basics. Cooling time depends on mass, surface area, and local convective flow. Insulation, trapped gases, or active internal sources, batteries, reactors, can extend cooling times dramatically. Lab studies of quenching in seawater show how complex film formation and violent instability affect heat removal. ROV and in situ sampling. Combine thermal traces with chemical sampling and visual inspection before breaching any hull. Essential is redundancy. Containment. Lift with distributed slings, quarantine on deck, and employ controlled venting and chemical mitigation for battery-related incidents. When the lights fade and you are 30 miles offshore with a recovered crate that still smells faintly of electrolyte, the sea gives you something else besides data, a reminder.
Recovering things from the deep isn't just about metallurgy and winches. It's about the small, careful acts of translating instrument numbers into human decisions. It's about the patience to run one more sample, the stubbornness to ask for a second opinion, and the humility to admit the first model might be wrong. The wreck itself, a charred test vehicle with a ruined battery pack, went into a secure facility for teardown. The manufacturer updated protocols. The salvage manual added an appendix on deep thermal events. For me, the memory that lingers is small and oddly domestic, the thermistor needle rising a fraction, a sound like distant waves in a shell, and the soft, professional silence of the team as we checked boxes and made a plan. The wreck was still warm when we found it, not because the ocean had forgotten time, but because chemistry, structure, and pressure had kept the heat trapped long enough for us to detect it and act. If you ever find yourself on a recovery detail, here's the line to remember. The deep prefers equilibrium, but when it refuses to cool, pay attention. Small numbers tell big truths.